Lagrangian mechanics. That's what we're doing. We're doing Lagrangian mechanics. And there are a bunch of awesome problems. So we need to like slowly build up what kind of problems we do. So I've done the pendulum, and then I did a block or bead on a wire with 3 different paths. In both of those cases, there was really just one degree of freedom. You could describe the system with 1 coordinate. So now we're going to do a problem where you have to use 2 coordinates to describe the system. So let me tell you the problem. Surprise, we already did this problem. If you're watching my playlist, I solved this problem back using work and momentum because I wanted to do it again so you could compare. I'll let you do the comparison. I'm just going to focus on solving the problem. So here's the problem. We have a wedge on a frictionless plane, and then we have a block on the frictionless wedge. So if I take that block and let it go, the block's going to slide down that way, but the wedge is going to move back that way. So both of them are going to move. It's not a trivial problem, but in Lagrangian mechanics, we can just say how these objects are constrained to move, and with that create a coordinate system, and then use the Euler-Lagrange equation to find equations of motion. So we define the Lagrangian as the kinetic energy minus the potential energy, and then this equation tells us how to get the differential equation of motion. Now, you may not be able to solve it, but you can get it. Okay, we could solve it here. So this says the partial of L with respect to one of the variables, and here I put Qi because we could have more than one variable. These are our generalized coordinates. Q are our generalized coordinates. And then I take the partial of L with respect to Qi dot, which is the time derivative of one of those coordinates. And then I take the derivative of that, and those 2 things have to subtract to be 0. That's the method. So the beauty here is that as long as we can pick some reasonable coordinates for this system, then we can write down our Euler-Lagrange equation. So let's do it. Okay, I'm going to say that this wedge has already moved a little bit, and that's my origin. You can really pick anything. You can get anything to work. So I'm going to call this x1, the location of the edge of the wedge, the edge of the wedge, the edge of the wedge. And then I'm going to call this distance S. So those are my 2 generalized coordinates, x1 and S. And I'm calling it x1 because I am going to need the x and y position of the mass, but not all the way. Okay. You could pick other coordinates too, right? But this one seems to make sense because if I have any S and x1 value, I could tell you where everything is, right? Okay. So let's just go ahead and write down our kinetic energy term. So let's focus on that first. This term is pretty easy. I can write the kinetic energy of that one mass is 1/2 m1 x1 dot squared. Right? It just moves in the x direction, so its velocity is x1 dot. Square that 1/2 mv squared. That's pretty straightforward. But what about this one? If I want to use the value s, I don't know how to write the kinetic energy. So I need to get s in terms of real Cartesian coordinates x2 and y2. So I can actually say this is plus 1/2 m2 x2 dot squared plus y2 dot squared. And this is your key. We can always write the kinetic energy in Cartesian coordinates, the real Cartesian coordinates. And then I just need to make a connection between real Cartesian coordinates and my variable, and then I can get this in terms of my variable s. Okay, so let's get the x and y coordinates of this. I'm going to write x2. What's the x coordinate of this? Well, it's going to be x1, and x1 could be negative, right? x1. And I do make a mistake with the sign here at some point. So if I make a mistake, I'm telling you right now, it wasn't intentional, but I like to plow through, you know, like a superhero. I just made that move. I thought it looked cool. Okay, so if that is x1, what is this part up here? Well, I have to add onto this the x component of that thing right there. So that's going to be equal to plus, actually it's going to be minus s times cosine theta. Because s I'm measuring as a positive quantity up here, right? But since the wedge is that way, it's going to be minus. So that's my x. Now for my y, I'm going to say y2 is just the height of that. And that's easy. It's just going to be equal to s times the sine of theta. But now that I have those relationships for x2 and y2, I can take the derivatives, and then I'll know what to put in for x2 dot squared and y2 dot squared. So let's take the derivative of x2. x2 dot is going to be the derivative of x1, which is x1 dot. And then the derivative of this with respect to time, well, that's just a constant, so I just get s dot cosine theta. And then if I do the same thing for y2 dot, I get s dot sine theta. Now I'm going to need to square those and put them into my kinetic energy term. Let's just do that. T equals 1/2 m1 x1 dot squared plus 1/2 m2. Now I need x2 dot squared. So I can do this in one fell swoop, right? That's not too bad. So I can square this. I get x1 dot squared minus 2 x1 dot s dot cosine theta. Wait. OK, that's fine. So I'm just double checking here. That should be plus or minus. I told you I was going to make an error, so you can't be surprised. OK, so x1, and then I have to subtract. I think that's right. OK, carry on. So that's that cross term, and then I get this term squared plus s dot squared cosine squared theta. And then I have to do y dot squared, which is pretty easy. It's just this, plus s dot squared sine squared theta. Well, we have some simplification, so let's just get to it. I have a 1/2 m1 x dot squared. I have a 1/2 m2 x dot squared. And just because I want m1 and x2 are, m1 and m2 are constants, I'm going to combine those together. So I have 1/2 m1 plus m2 x1 dot squared. Now I'm going to have this term right here that's going to be minus 1/2 times 2, so those cancel, m2 x1 dot s dot cosine theta. Now over here, I'm going to get 1/2 m2. Here I have an s dot squared cosine squared theta plus s dot squared sine squared theta. I can factor out the s dot squared, and then I have cosine squared plus sine squared is 1. So this is just going to be plus 1/2 m2 s dot squared. And that's my kinetic energy term. OK, let's just go ahead and write down the potential energy term. So here, again, we're going to use a slight trick. I'm going to say U is m2 gy2. Now, that's wrong if I put my origin right there, because this mass has some center of mass and it has a potential energy. But when we use the Euler-Lagrange equation, we're going to be taking derivatives. So if it's a constant term, it's just going to drop out. So I'm just going to not even put that there. And I know it's kind of cheating. I said I was going to cheat. It's fine. If you say you're going to cheat and then you cheat, it's OK. So this is just going to be equal to m2g, and then y2 is s sine theta. OK, so let's put our whole Lagrangian together. I'm going to write it up at the top. I think I can remember that. So let's just erase this, because we're going to use it. I want it at the top. So it's like prominently displayed. L is going to be 1/2 m1 plus m2 x1 dot squared. And then I have this. I'm going to put this one next. Plus 1/2 m2 s dot squared minus m2 x1 dot sine s dot cosine theta. And then I have my potential energy term. So minus the potential energy. So it's going to be minus m2 g s sine theta. Is that good? OK. So now I can erase this. So here we have something new, right? Because I have two variables. I have x dot. I don't have an x. I have s dot. So we're going to have to write down, do the Lagrangian equation twice. Let's just start. I'm just going to start with, I'm going to start with s. So let's do this, partial of L with respect to s. I'm going to go through here and I'm going to find any s terms. No, No, S dot doesn't count. It's got to be S. No, there's only one right there. So if I take the partial of that with respect to S, I get negative m2 g sine theta. Now let's take the partial of L with respect to S dot. Okay, looking for S dot terms. Nope, there's one. So if I take the derivative of that with respect to S dot, the partial, the 2 comes down and I have 2 over 2 is 1, so I just get m2 S dot. Okay, keeping along, oh, there's another one. So if I take the derivative of that, it's just to the first power, so it goes away. So I get minus m2 x1 dot cosine theta, and then there's no other terms. So now I have to take the actual time derivative, so I'm going to write this out. d dt, the partial of L with respect to S dot, is equal to, okay, the derivative of this with respect to time is going to be just the derivative of S dot with respect to time, so that's m2 S double dot. And then over here I have minus m2 x1 double dot cosine theta. Because remember, theta is a constant, m2 is a constant, and so forth. So putting those two together, I have this minus this is equal to 0, or this is equal to this. So let's just write that out. So I have m2 s double dot minus m2 x1 double dot cosine theta equals negative m2 g sine theta. Okay. Now, I mean, we're kind of at a quandary here because we have a second derivative of s and a second derivative of x. And so let's just table that for a second. Let's put that off to the side. I'm going to just rewrite it over here so it's out of the way. m2 s double dot minus m2 x1 double dot cosine theta equals negative m2 g sine theta. I'm going to put a box around it to protect it. Now it's protected. You can barely see that. Okay. Now we can go back up to our Lagrangian and do the x. So the partial of L with respect to x, that's our other variable. Okay, I'm going to go through here looking for x's. That's the x dot doesn't count. No, x dot doesn't count. Nope. Okay. And this is kind of a big deal, right? Because if it doesn't depend on that coordinate, then when I do the next one, the partial of L with respect to x dot, this is x1. Okay, let's just go ahead and do that. Here, this is pretty easy. I get m1 plus m2 x1 dot, because it's power rule. There's no x1 dot there. Oh, there's one right there. Minus m2 s dot cosine theta. So I don't even have to take the derivative, right? Because remember, the partial of L with respect to x1 minus the derivative with respect to time partial of L with respect to x1 dot is equal to 0. But that's 0, then this is 0. And if the derivative is 0, then this has to be equal to a constant. So let's just call this a constant c. And let's go ahead and find what that constant is, right? So I know that if I release this from rest, my initial x velocity is 0, and my initial s velocity is 0. So at time t equals 0, that's 0, and that's 0. So that means that that has to be 0. Okay, so now I have a relationship between x dot and s dot, and I have a relationship between s double dot and x double dot. Let's go ahead and solve this for, I'm just going to do it the same way I did it before. Let's solve this for s dot. So I'm going to solve that for s dot. I get m2 s dot cosine theta equals m1 plus m2 x1 dot. And now I'm going to divide. So s dot is going to be m1 plus m2. Although you can kind of see right here what this says, right? This is kind of, it's not quite, but it's going to be conservation of momentum because that's the velocity of the wedge. That's not the velocity of the other block because it's the it's that s property. But let's just keep going. So x1 dot over m2 cosine theta. Is that what I did before? Yep. Okay, good. We're on the right track. Okay, now if that's s dot, and here I have s double dot, I could just take the derivative of both sides of this equation, right? That's a dot. So if I take the derivative of this, I get s double dot. If I take the derivative of this, well, that's a constant, that's a constant, that's a constant, so I just get that. So that's kind of nice. Now I have a relationship, I have two relationships between s double dot and x double dot, x1 double dot. So let's just substitute that in over here and get an expression just for x double dot. So if I put that in up here, I just get m2 times this, and the m2's cancel. So I get m1 plus m2 x1 double dot over cosine theta. Right? Because if I put in this, m2 times that, the m2's cancel. And then I have this term minus m2 x1 double dot cosine theta. And then I have this minus m2 g sine theta. Now I have a differential equation that only depends on x double dot. And you can see that x double dot is going to be a constant, so you could actually integrate this. I'm not gonna, but you could. Okay, so let's just solve this for x1 double dot. We can do it again in one fell swoop. I think that's good enough. I can factor out the x1 double dot. So I have x1 double dot. And then on the other side, I have this negative m2g sine theta. And then I have to divide by all this stuff, right? So let's just do that. m1 plus m2 over cosine theta, that's that term, minus m2 cosine theta. And yeah, it's messy, and you can probably simplify it, but I think it's okay. So now that we have x1 double dot, it's a constant. That means we have s double dot, a constant. So we really solved the whole problem. And you could integrate both sides. Of course, I'm going to do it numerically just because it's a little bit more fun to plot that way. Let's just check something, right? Because what if mass 1 is ginormous? If mass 1 is giant, then this shouldn't accelerate, right? So if that's the case, let's just see if x1 double dot is 0. So here I have m1 plus m2, and that's very large. So this whole thing's going to be something like m1, which is very, very large. And take a number m2, which is small compared to that, and divide by this. It's going to be close to 0. So that seems reasonable that would be the case. You can go down here and do the same thing and find that the acceleration of s would be mg sine theta, m2g sine theta, or g sine theta. But I'm not going to do that. I think it works. Let's go ahead and make a numerical calculation. And so we're going to do the same thing we've done before. If I pick my initial conditions, I can say x1 double dot is delta x1 dot delta t. And here I have a problem. I'm using these subscripts for more than one thing. And then I can say that's going to be x1 2 dot minus x1 1 dot over delta t. So I can update x1 dot. x1 2 dot is x1 1 dot plus x1 dot double dot delta t. And then I can do the same thing for x1. x1 2 equals x1 1 plus x1 dot delta t. So it's something we've been doing before. Okay, our normal numerical calculation. Let's just jump in Python and see if we can get this thing to work. Okay. Now, remember, I'm going to write this down because it's going to be important at the end. Remember, if I want to find the actual x and y positions of this, in particular the x position, x2 is actually going to be equal to x1 minus s cosine theta. Right? I'm going to use that. And then we also have x2 dot. The velocity is x1. We don't need that. Let's just go. Python time. Okay. Switching to Python. And again, it's not that you couldn't integrate and find everything out like that, but I think if I want to make a graph, I'm going to use Python anyway. And we're going to be doing problems where the differential equations are not trivial, and so this is a good habit to get into. It's just the way we do things in the real world. We use computers to solve problems, It's just as legitimate as an analytical one, no matter what you think. Okay, so G1 equals graph. I'm going to need a graph. X title equals time. Y title equals, let's just plot X. Yeah, we're going to plot time versus X. And then I'm going to give it a width, spell it right, equals 400. A height equals 200. And then I need two graphs. F1 equals G curve. Color equals color dot blue dot equals true. Don't actually need that. F2 equals G curve. Color equals color dot red dot equals true. But it looks nice. Okay, M1, let's say, is 2, and M2 is 1. I'm just picking some values here. Theta, I'm going to pick it as 35 degrees. I'm just picking it, times pi divided by 180. G, 9.8. What else do I need? T equals 0. dt equals 0.01. Okay, so now I have my I need to make my variables that I'm going to plot. And I'm going to need my initial values for my variables. I need my initial s and x1. So s is going to be equal to, let's start at that 1, right? I'm measuring from the bottom, so I have to give it some value. X1 is 0. S dot, I do need an initial velocity, 0. X1 dot, 0. Okay, I think we're ready. So now let's just do a time loop. So let's say while t is less than 1. I could do it while s is greater than 0, but I don't like to do that because it's possible I get the sign wrong and it moves further away, and then my program never ends, and awkward. Okay, so I don't want to do that. I am going to do a rate so that it will take 1 second to run the thing, and we can watch it. It'll be fun. So now I'm just going to calculate s double dot and x double dot. So s dd dot, d dot is double dot. That's what I call it. You can call it whatever you want. I'm looking over here at my equation right here, and I'm just going to type in that equation. M1 plus M2, M1 plus M2 times x1 double dot. So I need to do x1 first. So let's just skip up here and do that first. X1 double dot equals, now I'm going to use my other equation, which is right there. You can barely see it. Negative M2g sine theta, negative M2 times g times sine of theta, divided by, I got a mess. And you could simplify that. I said that. M1 plus M2 divided by cosine theta. And then minus M2 cosine theta. Okay, and then this s double dot is that times x1 double dot divided by M2 cosine theta. Okay, so now I have the double dots. I can update the dots. So x1 dot equals x1 dot plus x1 double dot times dt. S1 s dot equals s dot plus s double dot times dt. Now I can update the values. X1 equals x1 plus x1 dot times dt. S equals s plus s dot times dt. And then t equals t plus dt. Okay, now I want to plot the actual positions. So let's do that. I'm going to plot f1 dot plot is easy. It's just going to be equal to t and x1. And then the other one, I need to actually calculate x2. So x2 is going to be equal to x1 minus s times cosine theta. So now I can plot that, f2 dot plot t x2. Is it going to work? You never know. You just never know. I think it works. Okay, now let's try the special case, right? I know that if the masses are equal, they shouldn't move the same amount, but they'd have the same velocities. Let's just plot. Let's print at the end the final momentum of the two things. If they have equal and opposite momentums, we know momentum's conserved, and it should be conserved, and that's a win, and we'll end right there. Okay. So I'm going to go down here, after the whole thing's over, I'm going to print P1 equals, the momentum for object 1 is going to be mass 1 times its velocity, which is x1 dot. Now, if I'm doing this after the loop, it's the velocity at the end because I've already updated it. And it would be technically in kilogram meters per second, but we don't really have to do that. Print P2, this is x, I'm going to put the x because we're just doing the x momentum. It's going to be equal to m2 times the x2 velocity. So actually I do need this because I never calculated that, right? I have s velocity, but the x2 velocity is going to be the derivative of this. So it's going to be equal to, I'm going to just print this as x1 dot, that's the derivative of that, minus s dot times cosine theta. And that would be in kilogram meters per second. Oh, that's a double high five. Okay. So it works. Looks like it's good. Saving this. Now, I do have, if you want to go back and look through my playlist, I'm not going to do it. I'll probably put a link to that. The previous time I did the wedge, I actually modeled the wedge as a block, and there was a spring force between them. And so I didn't use Lagrangian mechanics. I used just weird stuff. And it looked like it worked. I'm not 100% sure. But if you can get those two programs to agree, that'd be a great homework assignment for you. But I'll let you do that. We'll, of course, do some more Lagrangian problems later. So stay tuned. If you're all the way to the end and you're curious, yes, I put a link to the playlist for this whole classical mechanics series down below, so you can go look through the whole thing and let me know if you have any questions. I am happy to answer them, and I will talk to you later. Bye.